Welcome to The Explainer. We're here to break down tricky topics into something anyone can understand.
All right, so today we are tackling thermal radiation. We're going to start with a simple question. How does heat jump across empty space? Then we'll get into this idea of a universal glow. After that, we'll see how scientists use a perfect model, a blackbody, to understand it. Then we'll bring it back to the real world before looking at how this whole thing warms our planet.
Okay, let's just jump right in. And we'll start with a puzzle, one that you've definitely come across, even if you didn't really think about it at the time. Okay, so picture this. You're standing near a campfire. You can feel that intense heat on your face, right? Even though the air between you and the fire might be chilly. Or think bigger, way bigger. The sun. It's 93 million miles away, across the total vacuum of space, yet it warms your skin. So, what gives? How is that heat making the trip if there's literally nothing in between to carry it?
Well, the answer comes down to the three ways heat gets around. You've got conduction, that's heat through touch, like grabbing a hot pan handle, ouch. Then there's convection, which is heat moving through fluids, like the rolling boil in a pot of water. Now, the key thing is, both of those need stuff. They need a medium, a solid, a liquid, something to travel through. But radiation, that's the odd one out. It's just pure energy, moving as a wave. It doesn't need any medium. And that's why it's the only one that can make that impossible journey through the vacuum of space.
So yeah, it's all because radiation isn't matter. It's just pure energy. And it's traveling in these invisible ways that, and this is the crazy part, are being shot out by, well, everything.
These waves belong to the huge electromagnetic spectrum. I mean, this thing covers it all, from the radio waves that bring you music all the way up to super high-energy gamma rays. The little piece of that spectrum that we care about for heat is what we call thermal radiation. And that itself is a band that includes infrared, all the colors of light we can actually see, and even some UV.
And here is where it gets really wild. See, this means that anything and everything, with any temperature at all, anything above absolute zero, is constantly glowing. I'm not kidding. Right now, you are glowing. The desk in front of you is glowing. The walls of the room are glowing. The only reason we don't see it is because our eyes aren't built for it. Most of that glow is happening in the infrared spectrum.
So how do physicists think about this? Well, they see these waves as a stream of tiny little energy packets. They call them photons. And there's a really simple rule to remember. The shorter the wave, the more punch each photon packs. It's exactly why short wavelength UV rays from the sun can actually give you a sunburn, but the longer wavelength infrared rays just feel warm. And just to put that into perspective for you, the light our eyes can actually see, it's a sliver. I mean, a tiny, tiny fraction of the whole thermal radiation spectrum. That glow we were talking about from everyday objects, it's happening across a much, much wider band that's completely invisible to us.
Okay, so if everything is glowing, how on earth do you measure that? How do you compare the glow of a person to the glow of a hot stove? Well, to get a handle on it, physicists needed a benchmark, a perfect, idealized model they could use as a kind of universal yardstick. And what they came up with is called a blackbody. Now, this isn't a real object you can hold, it's a concept. An ideal object that does two things perfectly. It absorbs 100% of any radiation that hits it, and because of that, it's also a perfect emitter of radiation. Think of it as the ultimate radiator. Nothing in the real world can emit more heat at a given temperature. It sets the upper limit.
And there's a pretty brilliant way to think about this. Imagine you have a hollow box, and you poke a tiny, tiny hole in it. Any light that happens to fly into that hole is going to bounce around and around on the inside, getting absorbed a little more with each bounce. The chance of it finding its way back out that tiny hole is practically zero. So that little opening, it's a perfect trap for light. It behaves almost exactly like a theoretical blackbody. Now, figuring out the blackbody gave us two super important laws. The first one is the Stefan Boltzmann law. This one is all about the total amount of energy being pumped out. And what it says is that the energy an object radiates is proportional to its absolute temperature, to the fourth power. That's huge. It's not a simple one-to-one relationship. This thing is explosive. And that T to the fourth relationship is just wild. Here's what it means in practice. If you double the temperature of something, it doesn't radiate twice the energy. It radiates 16 times more energy. A tiny little nudge in temperature results in a massive fire hose of radiated heat. Okay, so that was the amount of energy. The second big law, Wien's displacement law, tells us about the color of that energy. It's simple. As an object gets hotter, the peak wavelength of its glow shifts shorter and shorter to more energetic waves. And you've seen this. This is why a blacksmith's piece of iron goes from glowing invisibly in the infrared to a dull red, then a bright orange, and finally to a brilliant white hot as it heats up. But let's be real. We don't live in a world of perfect theoretical objects. So how does all this apply to the stuff we actually interact with every day? First thing to get straight, a blackbody is a physics concept. It's not just about the color black. Your black t-shirt looks black to your eyes because, yeah, it soaks up most of the visible light that hits it. But if you could see in the infrared spectrum, that same shirt might actually look like a shiny mirror, reflecting most of the heat. So how it behaves with thermal radiation is a whole different ballgame compared to an ideal blackbody. So to deal with real-world messiness, we have a property called emissivity. It's basically a score, a number between 0 and 1. It just tells you how well a real surface radiates energy compared to our perfect blackbody at the same temperature. So a perfectly shiny polished mirror, it's a terrible radiator, so its emissivity would be close to 0. Our perfect blackbody, it's the champ, so it gets a 1. Okay, think about an opaque surface, something you can't see through. When radiation hits it, it's gotta go somewhere. Only two things can happen. It either gets absorbed by the surface or it bounces off. It gets reflected. That's it. So the fraction that gets absorbed, we call that absorptivity, plus the fraction that gets reflected, reflectivity, they always have to add up to 1. All of it is accounted for. And this is where things get really clever in the real world. Take a look at white paint. For solar radiation, sunlight, it has super low absorptivity. It reflects most of it away. But, and this is the cool part, it has a really high emissivity. That means it's fantastic at radiating its own heat out. See the difference? That's exactly why we wear light colors and paint roofs white in hot places, to stay cool. On the flip side, you have something like black chrome, which is engineered to do the exact opposite. It's made to soak up the sun and hold on to that heat. All right, let's take this idea, this selectivity about which wavelengths get absorbed and which get emitted, and scale it way, way up. Let's talk about the biggest example there is, planet Earth and its atmosphere. You know the greenhouse effect, right? That feeling in a car that's been sitting in the sun? That same principle works for the whole planet. And it all hinges on this simple idea. Some materials, like the glass in your car or certain gases in our atmosphere, basically act like a one-way door for radiation. So here's the play-by-play. Step 1. High energy, short-wave radiation from the sun comes down and passes right through the atmosphere, no problem. Step 2. The ground, the oceans, they soak up that energy and they warm up. Now step 3 is the key. Those warmed-up surfaces then radiate that heat back out. But here's the catch. They're much cooler than the sun, so they radiate at a longer, lower energy wavelength, mostly infrared. And finally, step 4. The atmosphere, which let the sunlight in, is actually opaque to this outgoing infrared energy. It blocks it, it traps it. And that trapped energy warms the planet just like a blanket. So, there you have it. From something as simple as the color of your clothes on a hot day, all the way up to the climate of our entire world, this invisible energy is constantly at work, shaping everything around us. It makes you wonder, what else might it be secretly controlling?